How do you dig a tunnel beneath a city without making the city above collapse? Think about what is sitting on top of that ground. In New York, it could be apartment towers, subway lines, water mains, gas pipes, power cables, traffic, and people walking across the street with no idea what is happening below them. In Los Angeles or Seattle, the same problem exists under freeways, downtown blocks, rail lines, and rivers. Now imagine a machine underground, longer than a football field, slowly removing thousands of tons of soil and rock from beneath all of it. Every foot it moves forward creates empty space, where solid ground used to be. So why doesn't the street sink? Why don't buildings crack? Why doesn't the tunnel fill with water or cave in before it is even finished? The answer is not just digging. It is controlled pressure, steel, concrete, sensors, and one of the most precise machines ever built. That is why tunnel construction under a major city is never just about cutting dirt. A tunnel may need to pass beneath a river where water is pushing in from every direction, through rock that can resist steel for miles, or under a downtown street where one wrong move could damage roads, utilities, and foundations. Above the machine, life keeps moving. Cars cross intersections. Trains run. People work in offices. But below them, engineers are trying to create a hollow space inside ground that does not want to stay open. On paper, it sounds almost impossible. The machine built for that job is called a tunnel boring machine, or TBM. From the outside, it looks like a giant steel cylinder pushed into the earth, but inside it is closer to a moving underground construction site. It has electric motors, hydraulic systems, conveyor belts, control rooms, sensors, and mechanical arms working in a tight sequence. Its job is not only to dig forward, it has to cut the ground, hold back pressure, remove the material, and begin building the tunnel behind itself at the same time. That is what makes it different from any ordinary excavator. Above the tunnel, the city is not just sitting still. It is layered with weight, movement, and hidden infrastructure. There may be skyscraper foundations pressing deep into the ground, old subway tunnels nearby, highway columns, storm drains, gas lines, water mains, power cables, and communication networks packed into the same underground space. On the surface, traffic keeps moving, and people continue their day like nothing unusual is happening. But below them, the TBM has to advance without disturbing that balance. It is not only cutting through soil, it is working underneath an entire living city, where even a small mistake can travel upward. The real problem is that the ground does not like empty space. Before the machine arrives, every layer of soil and rock is locked in place by pressure. Gravity pushes down from above. The surrounding earth pushes inward from the sides. Groundwater looks for any weakness where it can force its way through. The moment material is removed, all of those forces try to close the gap. Loose sand can flow. Clay can deform. Cracked rock can break free. Water can rush in faster than workers could ever control by hand. So the danger is not simply digging too slowly or too quickly. The danger is creating a space underground before the machine has a way to hold that space open. If too much ground is removed before the tunnel is supported, the surface can begin to settle. At first, it may be only a few millimeters, but in a dense city, a few millimeters can matter. A road can crack, a sidewalk can dip, a buried pipe can shift. In the worst cases, the ground can open into a sinkhole. Nearby foundations may not fail immediately, but they can lose support unevenly, and that is where real damage begins. For tunnel engineers, collapse is not a dramatic surprise. It is a pressure problem that must be prevented before anyone above ever notices it. At the very front of the TBM is the part that takes the first hit. The cutter head. It is a huge rotating steel face, built with cutting discs, scraping blades, and hardened teeth arranged across its surface. But it does not spin like a drill in a hardware store. It turns slowly, with enormous torque. That slow rotation is the point. The cutter head presses into the ground with enough force to break rock, scrape through soil, and keep the machine moving forward one controlled bite at a time. From the outside, it looks simple. Underground, it is where the fight begins. What happens next depends on what the machine is cutting through. In hard rock, the cutter discs do not slice the stone like a knife. Instead, they press against it with extreme force, creating tiny fractures deep inside the rock. As those cracks spread and connect, pieces break away from the face and fall into the machine. But soft ground is a different problem. Clay can smear, wet sand can flow, loose soil can move like liquid if it is not controlled. In that kind of ground, the cutter head is not just opening a path. It also becomes part of the system that holds the tunnel face steady before the earth has a chance to collapse inward. But this raises the most important question in the entire process. If the cutter head is opening a massive space at the front of the machine, why doesn't all that loose ground simply rush into the tunnel? Why doesn't wet sand collapse forward or groundwater force its way through the face? The answer is that a modern TBM is not just removing earth. It is replacing the pressure of the ground with pressure of its own at exactly the right moment. One of the main ways this is done is with an earth pressure balance system, often called an EPB machine. Instead of throwing the excavated soil away immediately, the TBM keeps part of it inside a sealed chamber just behind the cutter head. That chamber is not empty. It is filled with the same soil the machine has just cut, mixed, and compressed until it behaves like a dense plug. Hydraulic systems then control how strongly that material pushes back against the tunnel face. If the ground outside is pressing inward, the chamber pushes outward with matching pressure. At the same time, a screw conveyor slowly removes the soil from the chamber at a controlled rate, so the machine is digging, supporting the ground, and managing the pressure all at once. But the balance has to be exact. If the pressure inside the chamber drops too low, the ground ahead of the machine can start moving toward the empty space. At the surface, that movement may show up as a dip in the pavement, a cracked road, or, in serious cases, a sinkhole. But if the pressure is pushed too high, the opposite problem can happen. The machine can force the ground upward, lifting pavement, stressing buried utilities, or putting uneven pressure on nearby foundation stones. That is why operators do not treat pressure as a rough estimate. Underground, a small mistake in pressure can become a very expensive problem above ground. In ground that is too wet or unstable, engineers may use a different type of machine called a slurry TBM. This is common when a tunnel has to pass under a river, a harbor, or soil packed with groundwater. Instead of relying only on excavated dirt to hold the face, the machine pumps a thick bentonite slurry into the front chamber. This fluid pushes back against the ground and seeps into tiny spaces between sand grains, forming a thin protective layer. That layer helps seal out water and keeps the tunnel face from falling apart. In places where water pressure could destroy the excavation, the slurry becomes the shield that holds everything in place. Once the ground is cut, the machine has to move it out. But it cannot simply open a door and dump everything behind it, because that would destroy the pressure balance at the face. In an EPB machine, a heavy screw conveyor pulls the excavated soil out of the pressurized chamber little by little, almost like a controlled valve. From there, the material can drop onto long conveyor belts running through the tunnel or into small rail cars that carry it back toward the surface. Every ton removed has to match the machine's advance. Too fast, and the ground can move. Too slow, and the machine can overload itself. While the cutter head is opening the ground in front, another operation is happening just behind it. The TBM is not leaving an unsupported hole behind. Inside the protection of a steel shield, a mechanical erector arm begins building the tunnel wall almost immediately. It lifts heavy curved concrete segments, rotates them into position, and locks them together one by one. Each segment is shaped to fit with the others until they form a complete ring around the tunnel. That ring comes the permanent structure that holds back the earth. So the machine is not just digging a path through the ground, it is cutting the opening and building the tunnel at nearly the same time. Then comes a question most people never think about. How does something this heavy actually move forward underground if it does not drive on wheels like a truck? The answer is that the TBM pushes against the tunnel it just built. After a concrete ring is locked in place, Powerful hydraulic jacks extend from the back of the machine and press against that ring. The ring does not move because it is already braced against the ground around it. So when the jacks push backward, the entire machine slides forward. In a strange way, the TBM uses its own finished tunnel as the surface it needs to keep advancing. This cycle repeats again and again. The cutter head breaks the ground. The muck is removed at a controlled speed. Concrete segments are placed into a new ring. Grout is injected into the space around that ring. Then the hydraulic jacks push the machine forward and the process starts over. One cycle may only move the TBM a short distance, but over time, those small movements become hundreds of feet, then miles of finished tunnel. Day after day, the machine advances through the dark while the city above continues, almost as if nothing is happening. But even if the machine can dig and support the tunnel, it still has to stay on course. Underground, there is no GPS signal, no sunlight, and no visible landmark to follow. A TBM can be working hundreds of feet below streets, rivers, or buildings, and still needs to arrive within a very small target zone. To do that, engineers use laser guidance, gyroscopes, automated survey stations, and onboard computers. A laser beam is projected through the finished part of the tunnel toward a receiver on the machine. If the TBM begins to drift even slightly from its planned route, the system detects it, and the hydraulic jacks can be adjusted to steer the machine back into alignment. One of the hardest situations for a TBM is mixed ground. That means the cutter head is not facing one clean layer of material. Part of it may be cutting through soft, wet soil, while another part is grinding against solid rock. The machine then receives uneven resistance across its face. One side wants to move easily, while the other side fights back. That can create violent vibration, heavy torque, and stress on the cutting tools. If the machine is not designed for that condition, it can drift off course, wear down its discs too quickly, or damage parts that are extremely difficult to reach underground. The worst situation is when something goes wrong at the front of the machine while it is already deep underground. If the cutter head is damaged or the cutting discs wear out in the middle of a drive, engineers cannot simply bring in a crane and lift the machine out. It may be buried beneath a river, a freeway, or an entire city block. In some cases, workers have to enter the front chamber under hyperbaric pressure, almost like deep-sea divers. They breathe special gas mixtures, pass through pressure locks, and work in a cramped, wet, dangerous space to replace the worn cutting tools by hand. A repair like that is slow, risky, and absolutely critical. To keep all of this under control, the TBM is operated from a sealed control cabin inside the machine. Operators watch live data from sensors across the entire system. Pressure at the face, torque on the cutter head, motor temperature, steering alignment, advanced speed, and the exact volume of soil being removed. That last number matters more than most people realize. If the machine removes more material than expected, it can be a warning that ground is flowing into the chamber. If that continues, the surface above could begin to settle. So every screen in that cabin is part of the tunnel's safety system. Even after the concrete ring is installed, the job is not finished. There is still a narrow gap between the outside of the new tunnel lining and the ground that was just excavated. If that space is left empty, the soil around it can slowly move inward to fill the gap. At the surface, that movement can turn into settlement, cracks, or uneven ground above the tunnel. To prevent that, the TBM injects fast-setting grout behind the ring as it moves forward. The grout fills the invisible space, hardens quickly, and locks the tunnel lining tightly against the surrounding earth. It is one of the quiet steps that helps keep the city above stable. After months, or sometimes years, of working through darkness, the TBM finally reaches the receiving shaft. On the other side, a concrete wall has been prepared for the machine's arrival. At first, there is only vibration, then small cracks begin to spread across the surface. The sound changes as the cutter head presses closer. Finally, the wall breaks open and the front of the machine pushes through, covered in mud, dust, and the marks of the ground it has crossed. For the engineers and crews watching, that moment is more than the end of a tunnel drive. It is proof that every calculation, every pressure reading, and every slow advance through the earth worked. The next time you ride through a subway tunnel, drive under a river, or pass beneath a mountain without thinking twice, remember what that space really is. It was not naturally waiting underground. The earth had to be cut, held back, measured, sealed, and supported inch by inch. Water had to be stopped. Pressure had to be balanced. Concrete had to be placed before the ground could move. And every sensor, every hydraulic push, every ring, and every adjustment had to happen in the right order. A tunnel is not just an empty path through the ground. It is a controlled victory over gravity, pressure, water, and time, built quietly beneath our feet while the world above kept moving.